There's a bunch of different types of factorizations. We actually just covered one of them. When we solve for ax equals b by multiplying both sides by the inverse of a, basically what we're doing is we're finding an x that would give you really a factor of b. So ax equals b. If you know a and you know b, and you're looking for x, basically you're really looking for the factors of b, right, given one of them already. So what we're dealing with here are situations in which you don't have any of the factors, right? So I don't know what the factors are of this matrix A. I'm starting from scratch. That, and you know, like, what do? You don't have an equation to work off of, so you're kind of in a jam, right? So it's kind of a, I mean, there's a bunch of different ways to go. I've seen different approaches for LU factorization. I mean, if you read through all this, it can be a little funky. But I have a little shortcut that kind of gets you through the approach first, and then once we get through the approach, we start working on understanding. Right? And so we're reducing A to an echelon form of U, echelon form U, by a sequence of row replacement operations if possible. Right? Let me just make sure this is on. One thing that's important is that we're not, for this algorithm to work, no row swapping. All right, and we'll talk about why down the line, but for this algorithm to work, that's a condition of it. All right, so U needs to be in the form of an upper triangular matrix. The stars represent anything that's a non-zero value, right? So basically, all the zeros below the main diagonal, all right? That's why I'm saying reduce A to an echelon form of U, right? Now, 2 is a little bit funkier. Place entries in L such that the same sequence of row operations reduces L to I. That's weird. I have something different for that. But I don't think I've ever quite been able to phrase it in a way that leads to concise steps. So you'll definitely want to follow along with this. All right, so echelon form. So let's start off with, well, I'll just work off of the row 1. We'll do a negative 1/3 R1 plus R3. And, you know, negative 1/2 R1 plus R2. I don't know what I'm circling. Okay, so 60, 30, 20 staying put. This doesn't matter which order I do it. Well, I wrote the blue one first, so I'll do the blue one first. So negative 1/3 of R1, so negative 20. Plus 20 gives me a 0. Negative 10 plus 15 gives you a 5. And then, unfortunately, negative 20/3 plus 12, so that's fun. But negative 20/3 plus 36/3, right? So 16/3. I think. All right. Then we have the 0. Ooh. negative 15 plus 20 is 5. And then negative 10, that is negative 10, right? Yeah, negative 10 plus 15 is 5 again. Negative, yeah. Let me just subtract that. Let me just double check. Negative 30. Right. Negative 15. Yeah. Yeah. Okay. All right. So not quite in upper triangular form. That 5 on the bottom has to go, but let's just sit tight on that for a second. I like to simultaneously, and this is where you'll see why I'm still working on how to phrase this or organize it in such a way that it would be like step 1 do this, step 2 do that, step 3 do that, and then voila, you get the final answer and everybody understands it and it makes perfect sense. Right? And in fact, if you go through YouTube channels, textbooks, everything, it's like, all right, so step 1, do this. Step 2, do LU factorization. Step 3, get your answer. You're like, oh, hold on, where's the LU factorization? Where's that part come into play? That's where I'm struggling. All right, so at a minimum, though, for my lower triangular matrix, I should be able to get the structure of it set up. What we're trying to do is get our U down. We're trying to reduce it mathematically down to the upper triangular form, so 0 is below the main diagonal, which should all contain 1s when all is said and done. All right? But for the lower, we're going to assume the upper triangle. The lower triangle is some numerical values, but the upper triangle itself is going to be all 0s. So we're just putting it in. All right. So step by step, what we do, once we zero out all the entries below the first pivot value in the first row, I guess definition of first pivot value, we'll be ready to move on to the second row, second column in a second. But what we're going to do is go back to our original matrix, divide each entry by the pivot. All right, so divide each entry in column 1 by the pivot of column 1. Right, so the pivot, I mean, once you start reducing it down into the upper triangular form, the pivot is the 60. Right, whether it's in reduced row echelon form or not, it's pretty obvious. The first non-zero entry in row 1 is going to be the first entry in column 1. Right, so, but if you go back, so now that we know where the pivot is, you go back into that original matrix, we would say, okay, what is 60 divided by 60? 1. What is 30 divided by 60? 1/2. What is 20 divided by 60? 1/3. All right, so 1, 1/2, 1/3. All right, so we're assuming the zeros in the L matrix. We're assuming the zeros in the upper triangle. It's everything else that we have to come up with numerically. Right? So the row reduction technique is for the purpose of identifying pivots, which in theory should be along the main diagonal. But we also need something to divide into that. So let's go into let's carry out the process of getting the U matrix a little bit more reduced. So in order to get this guy to become a 0, I'm going to do negative R2 plus R3. So 1/3. All right, so we take a step back, look in the previous matrix, divide each entry, each relevant entry, because we already know what the upper triangle in my L matrix is going to be. It's all zeros. So we're ignoring all of those. Anything that's relevant, we're going to divide by the pivot value. So in the previous matrix, I'm dividing each entry by the pivot value in column 2. All right, so and that's where my, the wording of the process kind of falls apart, because it's like divide each entry by the pivot value of column 2. Well, that's not really true, because I'm not dividing the 30 by the pivot value. Right? So, because that went to 0. So it's only the relevant values. So that's where things get a little kooky. Now, if I had a bigger matrix, if it were 4x4, 5x5, whatever, then I would continue the process. But I know what the pivot value is in my in this matrix. It's well in any of them, but I know it's at this 1/3. So I'm going to divide the pivot value by itself now, because that's the only thing that makes sense to divide. So 1/3 divided by 1/3 is 1. All right, so I have an L, I have a U. So let's see. Uh, 20. Ah, dang it. All right, I'll fix that. Maybe not. 0.5, 1, 0, 1/3, 1, 1. Ah, dang it. All right, so what we did essentially was we found 2 factors of the matrix A. One is in lower triangular form and the other is in upper triangular form. And again, this is just one way of determining factors of a matrix. But basically the idea is we're trying to find 2 matrices that would multiply to the given one. Because again, there's no such thing as matrix division. Right? If you were to try to just you try to divide two matrices on your calculator, even if the dimensions are exactly the same, the calculator tells you this, which is saying, what the hell are you asking me to do? I don't know what that means. Right? So it's not a thing. Right? So we defined an L and a U such that L times U is equal to A.